Hi everyone, today we'll start a new chapter which is applications of derivatives. Alright, so in today's lesson and the next lesson, we'll be learning how to use derivatives to sketch a graph. Alright, by sketching I mean to get the general shape of the graph. So for today's lesson, we'll be mainly discussing the theorems that are needed to know the shape. And today's will be more conceptual and more like the proof of those theorems. And the next lesson will be doing the actual practical graph sketching exercises. Alright, so if you are only interested to sketch a graph, you can directly proceed to the next lesson. Alright, so we'll start with a revision to the tangent line problem. So in the last chapter, we said that in order to find the equation of tangent to the curve at a point, then we need to find the slope of this tangent line, right? And in order to find the slope of this tangent line, we need to evaluate this limit, okay, h approach 0 plus h minus f of x over h, which is the first principle of derivatives. So the slope at this point is just the same as f prime of x naught. So we somehow establish a function called derivatives, which help us to determine is actually a function, a special function to find the slope of tangent line, to the curve. This is what we discussed in the last chapter, right? So in this chapter, in this particular topic, we'll be utilizing this property to find out the shape of the graph. And whenever we talk about sketching graph using derivatives, there are three things that we are concerning. Number one is whether the graph is increasing or decreasing. Okay, increase or decrease. Number two, we need to know where are the maximum and minimum points. Alright. Then lastly, we also need to know the shape of the graph, which in other words we say concavity, which is whether concave upwards, like a smiling face, a U shape, or an N shape, which is concave downwards, a sad face. Alright, so this is what we will be doing in these few lessons. Alright, so we'll start with the easiest one, which is increasing and decreasing functions. And by the name of it, I think you should know what they are about. And they are very straightforward. If you refer to the definition, increasing function means, let's say you have a function like this, okay, you have a graph, and then for the domain of this graph, you somehow have x1 and x2, then f of x1 is here, f of x2 is here. If you connect them together, then f of x1 is smaller than f of x2, which means the x value at the right will give you a greater y value. This is what we call as an increasing or decreasing function. Increasing function. And it doesn't matter how you connect them in the middle. You can connect it with a straight line. Okay, a straight line will do. Okay, some curvy line like this or some curvy line like this. It doesn't matter, as long as this point is greater than this point, then we call them increasing function. So similarly, if it is decreasing function, alright, you have x1, x2, x1 is here, x2 is here, you see? No matter how you connect, this is a decreasing function. Alright? So if you want to add the word strictly increasing and strictly decreasing, then this condition, f of x1 smaller than f of x2, has to be true for all the value of x in this interval, right? So for example, this is a strictly increasing graph. Okay, you have x1, x2, but this is not like x1. Okay, increase. Oh, this one I stay constant, then increase again. This is not a strictly increasing graph. All right. So the next one we'll be talking about is the monotonic functions. Monotonic means it is either increasing or decreasing. It cannot increase and decrease at the same time. So this is a concept of monotonic. Similarly, if you want to say it is strictly monotonic, then it has to be always increasing or always decreasing. Alright? So usually when we talk about the set S here, the interval, it can either be an open interval or a closed interval. But later on in the theorems, there are some times that we need to make it into an open interval, sometimes we need to make it into a closed interval. Alright? Then, alright, so in order to use all the derivative tests that we'll be discussing later, we need to make sure that the functions are monotonic, so that the trend, the concavity, the slope of tangent is not concerned, so that the trend, which means increasing or decreasing, and the concavity stays the same throughout that interval. However, 99% of the graph that we'll be sketching are not monotonic throughout the domain, which means the graph maybe look like this. And this is a cubic graph, right? Something like a cubic graph. As you can see, from here to here, oh, it's increasing. From here to here, oh, it's decreasing, then increasing again. So in order to sketch a precise shape, we need to split them into several parts, alright? So that from here to here, oh, it's always increasing, monotonic. From here to here is always decreasing, oh, monotonic. Again, from here to here is always increasing, monotonic. So our objective of doing the derivative test is to find these points, which are the critical points and inflection points, so that we can know the accurate shape of the graph. By the way, when we split them into several pieces so that they are monotonic, we call them piecewise monotonic function. Monotonic functions. Just a matter of terminology, alright? Okay, now we'll finally start with the first part of graph sketching, which is increasing and decreasing tests. We need to use derivative to determine whether the graph is increasing or decreasing. If you look at the theorems here, okay, you see we are taking the first derivatives. And what are first derivatives? First derivative, as said earlier, is the slope of tangent line. And tangent line, you know that it's always a straight line. It can either be like this, or even a straight line. So from the shape, I mean the trend of the tangent line, we can know either the graph is increasing or decreasing. Alright, so if you just read this theorem, you see that if the slope of the tangent line is positive, means it is like this, then it is increasing. Okay, if it is negative, means the graph is like this, therefore it is decreasing. And for this one is actually critical value, and we'll discuss it later. But before that, let's visualize the idea of this increasing and decreasing test by a very simple exercise, where we have to sketch the equation of tangent and determine the sign of the slope. Alright, so I repeat, the slope of the tangent line is the first derivative. So if you want to find the slope of at this point, this point, this point, this point, and you know that how to make a secant line become a tangent line, that is what we learned in the last chapter, right? With the concept of limits. Alright, so for the first one, the tangent line will look something like this. Am I right? Because the secant line is initially like this, right? Then slowly becomes like this. But this is not what we will be discussing today. Okay, today I will focus on the tangent line. Okay, then for this one, it is something like this. Then for this one, is the other way around, right? The other way around. And for this one, is like this. Maybe I need to adjust a bit, alright? So what can you notice here? For the first two curves, the slope of the tangent line are positive. Means f prime x is greater than 0. While for the third and fourth graph, the slope of the tangent is negative. Means f prime x is smaller than 0. So I split them into half. Okay, what do the first two have in common? If you notice, you see here, if I plot, if this is part of the graph, and I say that, okay, let's say like this is my x1, this is my x2. Do you notice that f of x2 is greater than f of x1, which means it is an increasing function. Similarly, for this one, you see your x1, x2, okay, your x2, f of x2 is also greater than your f of x1, which means it is also an increasing function. So I just write increasing on top. Alright? Then what about the third and fourth one? Okay, you see your f of x1 is here, f of x2 is here. Oh, it's greater than that. Okay, let me draw like this, x1, x2. This one is greater than this one. Hence, it is decreasing by our definition from earlier, right? Then what about the last one? Okay, your x1, x2. F of x1 is also greater than f of x2, which means it is also a decreasing function. Both of them are decreasing. So I write on top. Do you notice that when the slope of the tangent line is positive, it is always an increasing function, no matter how the shape it is concave upward, concave downwards, it doesn't matter. As long as the slope, which means the first derivative, is positive, then it is always increasing. Conversely, if it is negative, then it is a decreasing function. Alright? So with that in mind, if you look back at the theorem, it totally makes sense, right? If the first derivative is greater than 0, which means it is positive, in this open interval. This open interval means what? Maybe it is not true at point A or point B. I mean at the end points of this interval. Maybe it is not true. But as long as it is true within A and B, and it is increasing from A to B on an closed interval. Alright? So conversely, if it is negative, then in between A and B, and it is a decreasing function in the closed interval of A and B. The reason why I emphasize on open interval and closed interval is because for this particular theorem, it is necessary for it to be continuous throughout A and B, including A and B, but it is not necessary for it to be differentiable at exactly on point A and exactly on point B. We'll see why when we prove this theorem, alright? But before we prove this theorem, we need to go through a few things, alright? And by a few, I mean 2 theorems. The first one is the Rolle's theorem, okay? So suppose that we have a y equals to fx, continuous, closed interval AB, then differentiable, open interval AB, if fa equals to fb, then there is at least a point that f prime of c is equals to 0. What does it mean? It means if you have a graph something like this, okay, maybe like this, okay, then this is your point A, this is point B. If they are equal, okay, you see f of A equals to f of B, then there is at least a point in which f prime c equals to 0. F prime c equals to 0 means what? Means the equation of tangent have a slope of 0. Slope of 0 means the tangent line is a horizontal line. And for this one, likely we have a point where the tangent line is a horizontal line, isn't it? Then you said, maybe this is only true for this one. What if we have like oh, by the way, it has to be continuous, yeah? It has to be continuous. Maybe even a sharp corner, you see, it doesn't matter, even a sharp corner. And you know that sharp corner, it is not differentiable at this point, right? Then what about a complex polynomial graph? Ooh, something like this. Can you see? fa equals to fb. Then we have more than enough. We have more than one point that have a horizontal tangent line. So this is all Rolle's theorems is about. If you want to prove it, which I'm not doing here, if you want to prove it, then maybe you need intermediate value theorems. And you can combine Rolle's theorem and intermediate value theorems together to do a lot of things actually. But for today, because I will be focusing on monotonic functions, isn't it? So I will combine it with the next one, which is the mean value theorem. Alright? So the mean value theorem states that if we have a y equals to fx, then it is continuous, closed interval ab, differentiable, open interval ab, then there is at least a point in between a and b which follows this formula. Okay, we will go through this proof very quickly. Okay, let me have a new page. Alright, proof. I think I will directly start with this graph here. Okay, graph y equals to fx, and then we have 2 points. Okay, this point A, then B. Okay, then obviously this is your B, F, B, and then this is your A, F, A. Okay, and now what I do is I want to connect 2 of them together. Okay, maybe I use purple color. I want to connect 2 of them together, and I call it, this is actually a secant line, isn't it? A secant line, remember? From the first lesson in the last chapter. Okay, and I call this purple line gx, and I want to find the equation of this purple line. And luckily, this is a secant line, but not a tangent line. Secant line means we can directly find the equation from the graph because we already have 2 coordinates. We don't have to do the limits, we don't have to do first principle, we don't have to differentiate anything. Alright? So, you know that for a straight line, it is y minus y1 is m times x minus x1, right? So, if I call my purple line gx, and my reference point is this one, is point A, then I just minus fa is equals to slope, I still don't know yet, but I will know later, x minus my x1 is A. Okay, now my question is, who is my slope? And obviously, because this is a secant line, I can say that the slope is actually y2 minus y1 over x2 minus x1. So I rearrange this a little bit, I will get fa plus the slope of it will be y2 minus y1 x2 minus x1 times x minus A. Okay, and I think this is all that we need, which is, I write this as equation 1. Okay, now I want another function. that represent the height, the vertical difference between the original graph of fx and the secant line function gx, which means it is like this. Maybe I should enlarge it like this, like this. I want to find this distance because you can, as you can see, it is like changing throughout, right? And you know that there will always be a difference as long as I'm in between A and B. There will be no difference exactly on A and B, right? So as long as I'm talking about in between interval A and B, I'm safe to have a function. Maybe I call it hx, okay? hx. And it is defined by the vertical distance between F and G, and therefore I can write hx equals to fx minus gx. Okay, equation 2. I think this is the most colorful slide in today's lesson. Okay, and now we substitute equation 1 into equation 2. We'll have hx equals to fx minus the entire thing here, fa, which I think I just straight away open the bracket, fa minus fb minus fa over b minus a x minus a. Okay, I'm running out of space, so I move on to the next slide. Okay, let me copy down whatever we have there. Equals to fx minus fa minus fb minus fa over b minus a times x minus a. This is what we got from earlier. And now I will differentiate with respect to x. Okay, and you don't have to worry because both h and f are function of x, which means you don't have to do a complicated implicit differentiation. Okay, so h prime x equals to, you differentiate f, you get a f prime x. F of a is now a constant. You differentiate a constant, it becomes nothing. Okay, minus, what about this? The whole chunk here is also a constant, but we have an x here, which means we need to keep it as a constant multiple, b minus a. And you differentiate x minus a, you get a 1. Okay? And now, because if you remember the theorem, okay, we need to find out what happened at point C, right? So suppose we have a point C in between A and B, okay, when x equals to C, where C is in between A and B, then h prime C is f prime C minus this a constant, don't touch, over b minus a. Alright, now we will come back to this one. Okay, as you can see, exactly at point A and point B, what happened to our hx? H of A is equal to 0, right? There is no difference between the secant line and the original curve. What about at point B? H of B is also equals to 0. And then by Rolle's theorem, if FA equals to FB, in our case is HA equals to HB, then there exists a point C at which F prime C, in our case H prime C equals to 0. Come back to this. Now we know that H prime C is equals to 0. And we can say that 0 equals to F prime C minus FB minus FA over B minus A. And therefore, F prime C equals to FB minus FA over B minus A. And this is what we want to prove. Right, this is our mean value theorem. Another thing that I want you to take note on the mean value theorem is that it does not require f to be differentiable at either a or b, right? Because when we are drawing this secant line and the graph, one-sided continuity at A and B is enough, right? Means like as long as it is continuous from the right or continuous from the left, either one, it will be enough, alright? And when we discuss about differentiability, we say that it has to be continuous from both sides to be differentiable. But in this case, you see that it is not necessary for A to be in a closed interval, which means it is not necessary for it to be continuous from both sides. Alright? So this answers my question that why is the theorem for closed interval continuous but differentiable for open interval? Alright? Very interesting, isn't it? However, what does this has to do with increasing and decreasing function? Okay, we'll finally get to the proof for our theorem 1. Okay. Now I will write it's actually a very short proof for this. Okay. So let's say we have 2 points. Okay, let x1 and x2 be any point. Okay, there can be any point in a closed interval AB with x1 smaller than x2, means x1 is at the left hand side of x2. Okay, then by the mean value theorem, what can we say about it? Where was my... Okay, I will shift this b minus a to the other side. F of, instead of a and b, we have x2 minus f of x1 is the same as f prime c times x2 minus x1 for some c in between x1 and x2. Okay, so the sign of the right hand side equation, because we know that x2 is always greater than x1, which means this piece will always be positive, which means if this is positive, then the right hand side will be positive. If this is negative, means right hand side will be negative. Okay, therefore we can say that f of x2 is greater than f of x1 if f prime c is positive. Try to make sense of it. A greater number minus a smaller number will give you a positive number. So conversely, if f of x2 is smaller than f of x1, okay, it is only if f prime c is negative. A smaller number minus a greater number give you a negative number. Okay, so by this one means what? This one means what? F of x2 greater than f of x1 means increasing, isn't it? Means increasing. Then f of x2 is smaller than f of x1 means what? Means decreasing. And hence, if it is greater than 0, if the derivative is greater than 0, means it is positive, it is an increasing function on that interval. Conversely, if it is smaller than 0, means it is negative, and the graph is decreasing. Okay, so this is a proof for the increasing and decreasing test. Alright, the next concept that we need is the extreme values or extrema or maximum or minimum in order to sketch our graph. And generally there are two types of extrema, which is number one, local, or sometimes people call it relative extrema, and number two, global or absolute extrema. Alright? Again, this is all about the terminology, so yeah, just get used to the terms. Alright? So for local or relative extrema, whether they are positive, whether they are maximum or minimum, it means that it is the greatest values nearby as compared to the values nearby. And by nearby, I means from both left and right. Alright? So if you look at this point, alright, the one that I highlighted, it says that it is a local maximum because it is relatively greater than all the points around it, right? From the left and from the right. Similarly, if it is a local minimum, it is it is relatively smaller than the points around it. Alright? So if I want to say a random point, like for example, I say this one, the one in green, it's a local maximum because it is relatively greater than all the one in red. That is wrong, because it is not relatively greater than the points on the right. Alright? So in order for it to be a local or a relative extrema, it has to be from the left and from the right. Okay? Very easy to understand, right? Then what about global or absolute maximum and minimum? It's even easier to understand. Global or absolute minimum means global of x or absolute maximum is the greatest values of y throughout the entire graph. Alright? So if I say that, oh, this graph is this function is in between a and b on a closed interval, then the highest point, which is this one, the one at D, is my absolute maximum because it is greater than all the points in the graph, right? Similarly, for point A, okay, point A is my absolute minimum because it is smaller than all the points in this graph. Alright? So if you want to understand extrema in detail, which means you want to do the extreme value theorems, I think I will just briefly write to you, okay? Right for you, yeah? Because this one is the extreme value theorem. So extreme value theorem says that if we have a continuous function f, alright, and on a closed interval a, b, then f will have both absolute maxima and absolute minima in between, okay, in a, b. Actually by the look at it, you say that, oh, it totally makes sense, right? Because my graph is only defined on this interval, so of course I will have a absolute maximum or absolute minimum, right? But if you really want to prove this theorem, extreme value theorems, you need to use the properties of real numbers, right? You need to use the properties of real numbers, and you need to use something like the Peano's axiom, which is the one that you use to prove 1 plus 1 equals to 2. Not prove, the one that you define 1 plus 1 equals to 2. Right? So if you are interested to prove this, you can try on your own, and it is actually quite interesting about this extreme value theorem. Okay. So with that in mind, we'll proceed with the next one, which is to find extrema. Alright? And sometimes people call it a stationary point, or a critical point. And then from earlier, we also discussed that first derivatives is the slope of tangent line. So what if I have my tangent line look like a horizontal line or vertical line? The slope of this tangent line is 0, right? And the slope of this tangent line is undefined, isn't it? So by this theorem, if f has a local maximum or minimum value at c, then the first derivatives will be equals to 0 or undefined, which means it is something like this. You see, this is a local or absolute maximum minimum, right? And then it is the slope will always be 0, because at this point the tangent line will be a horizontal line. This is why it is called a stationary point, because the tangent line will not move around. It is always a horizontal line around that region. Alright? But here's the thing. There are only 3 places where we can have extrema, whether they are local or global. Let me have a new page, okay? So we have 3 places to have extrema. So number 1 is, of course, like when your f prime x is equals to 0, which means it is a horizontal tangent line, okay? And if you refer to this one, this graph, yeah, this is a horizontal tangent line, and both of them are local max, right? Local max and local min. Okay, then the second place that we can have an extrema is my f prime x is equals to undefined, which means it is not differentiable at that particular point. Like for example, I think I will just look at this example here. Do you notice that we have a sharp corner here? And if you remember what we learned in the last chapter about differentiability, when we have a sharp corner, the graph is not differentiable at that point, because the derivatives from the left is different from the derivatives from the right. However, if you look at this graph, this is actually a absolute maximum, isn't it? It is actually an extrema. So this is why our theorem, we need to include that our f prime x is undefined, even though we don't know how to differentiate at that point. Okay? Because it will only make sense to say that this is an absolute maximum if we include that into our theorem. Okay? Back to this. There are the last place that we can have an extrema, which actually have nothing to do with first derivatives, nothing to do with the tangent line, the slope of tangent line, which is the end point. Okay, end point of the domain of f. Do you notice that both the endpoint are extrema, whether they are absolute or local? Why? Because you just look at this one. This one is absolute minimum because it is like the smallest value among the entire graph. What about this? You see, from the left, if you look at from the left, it is always smaller than all the points on the left, right? Then what about from the right? There is no values on the right. There is no points on the right. So by default, we say that, oh, it is relatively smaller than the points around it. But there are only points on the left. Hence, it will always be a local maxima or minima if it is the endpoint of the graph. And sometimes it can also be the global or absolute extrema. Okay? There is another thing that I want to talk about this theorem. If you look at this theorem, you might find that the wording is a little bit weird, because usually people will say that, oh, if f prime of c is equals to 0 or undefined, then we have a local max, local min. Why is it not so? Because the converse of these theorems means if f prime c is equals to 0 or undefined, it is not necessary that we have a critical point at c. Again, if f prime c is equals to 0, yeah, it can be a critical point. It can also be an inflection point, which we will discuss later. And it can be neither critical or inflection. Okay, this is because, like for example, just a very typical example, you have something like a graph like this, and you know that at this point the tangent line look like this. Okay, my drawing is not so accurate. Okay, it's a horizontal line, right? So automatically we know that f prime at c is equal to 0 if this is point c. However, do you notice that this is not an extrema? It is neither maximum or minimum, right? But the first derivative is still 0. Hence, the theorem is purposely written like this so that it is true for all cases. And in fact, this point is actually an inflection point, which we'll discuss later. Okay? So far, we have learned how to use the first derivative to determine whether the graph is increasing or decreasing, and also to find the extrema, right? But for the extrema, we still don't know whether there are maximum or minimum. This is when we can use the first derivative test for local extrema, alright? So let me go through the theorem very quickly. If your f prime change from negative to positive, then we have a local minimum. If it changes from positive to negative, then it is a local maximum. If it doesn't change, means there is no local extremum at that point. How to make sense of this theorem? It kind of makes sense, isn't it? Don't worry, we'll look at this graph. Alright? So now I want you to focus on this one, from C2 to C4. Okay? Particularly this point. You know that this is a local minimum, and the slope of the tangent line at this point is equal to 0, right? Then what about the tangent line nearby? Okay, let me draw a random tangent line for this point and this point. Okay. So the tangent line looks something like this, right? Like this. Then for this one, it looks like this. Something like this. Just a sketch, yeah? Okay, wait. Am I sketching? Okay. So the slope of the tangent line from at the left is actually negative slope, right? For tangent. Then from the right, it is a positive slope for tangent line. As you can see, it changes from negative to positive. And if you look at this graph, this is a local minimum. From negative to positive. From decreasing function to increasing function. Decreasing, then now you want increasing. So definitely we will have a local minimum at that point. And that local minimum sometimes can be absolute minimum depending on the function and the graph. Okay. Similarly, for this one, okay, the one in green at C2, you see the slope of the tangent line from the left is positive. Then this one is negative. From positive to negative means from increasing to decreasing, you need a maximum point, right? So from this and also this theorem, we can determine whether an extrema is maximum or minimum by looking at the sign from the sign of first derivative from the left and from the right. This is why later on when we are doing the graph sketching, we'll draw the sign diagram. Alright, so for example, if I find that it has a critical point at x equals to 0, alright, then I go ahead and determine the sign of f prime x. Okay, so at the left hand side of 0, it is positive, means it is increasing. At the right hand side, it is negative, means it is decreasing. So automatically, I can know that, at x equals to 0, the function will have a local maxima. Alright, so this is all for the first derivatives. Alright, we'll now look at the last concept that we need, which is concavity. For now, I will skip the definition first. All you have to know for concavity is, if it is like this, means a U shape, means it is concave up. If it is like this, then it is concave down. Alright? So now we'll look at the second derivative test for concavity. Alright? So suppose that f is the twice differentiable function on an interval I, which means the function f can be differentiated 2 times. Alright, you will not get anything crazy. You will not have like sharp corner or vertical tangent line or oscillation. Alright, if the second derivative is positive, then it is concave up. If it is negative, then we say it is concave down. Alright, so to visualize this, we'll look at this slide. Alright, so the one on the left, you know that it is concave up, right? Then the one on the right is concave down. So now we will do a very simple activity. Okay, we need to sketch the graph of the first and second derivative of the curve. So for the one on the left, which is the one that concave up, for the first part, you see I purposely already draw a line to split them into 2. If we draw a tangent line, okay, simply draw a tangent line like this, alright? Or maybe another, maybe I shouldn't draw tangent line. Maybe I should draw triangles. Okay, triangle, the slope, right? I need to find the slope. Do you notice that the graph is definitely decreasing, so it is a negative slope for the tangent? And then what about the magnitude? Does it become more and more steep or less and less steep? It becomes less and less steep, right? So the magnitude should become smaller and smaller. So if you want to sketch the first derivatives, you know that it is a negative slope, right? Negative slope means it is somewhere below the x-axis. And what about the magnitude? It becomes closer and closer to 0. So it should look like this. Okay. Then for the one on the right, okay, it is increasing. It is increasing, so it is a positive slope for the gradient. I mean for the tangent line. And then the magnitude, you see, it becomes more and more steep. More and more steep means it is further away from 0. Hence, the first derivative should be somewhere above the x-axis because the slope is positive and it is going further away from 0. Alright? And now, we need to differentiate again. From the first derivative to second derivative, so what is the point of finding second derivatives? Second derivative is to find the rate of change of the first derivative, right? Just like how first derivative is to find the rate of change of the graph of f. So if we look at 2 of them, what they have in common is both of the first derivative are increasing, right? And because this is just like from a quadratic let's say this is a quadratic and then to a linear, so obviously we'll have a constant graph for the second derivative, right? But where is the graph? It is always increasing. The first derivative is always increasing. Hence, it should be above x-axis for both of them. Again, for part 1, okay? Part 1, the original graph is decreasing. So it has a negative slope for the tangent line. So the first derivative, the graph will be below x-axis. And the magnitude of the slope, it is getting less and less steep. Therefore, the graph should be going closer and closer to 0. Alright? Then for part 2, the graph is increasing. So the slope of tangent line is positive. Hence, the graph of first derivative should be above x-axis. And the graph, the original graph, becomes more and more steep. Hence, it is going further away from 0. And for both part 1 and part 2, the first derivative graph is always increasing. And by definition, second derivative is the rate of change of the first derivative. As both of them are increasing, means they always have a positive slope for the gradient, for the first derivative graph, and hence the second derivative the graph will be always above x-axis, which means they are always positive. Alright, so that's the story. Then for concave down is actually technically the same, just the inverse of it. So again, I'll repeat the story. For part 1, you can see it is increasing, right? It is increasing, so it has a positive slope. Means your first derivative should be above x-axis. And the magnitude is becomes smaller and smaller because it becomes less and less steep. So the graph will look something like this, closer and closer to 0. Then for part 2, the graph itself is decreasing, which means negative slope for tangent. So the first derivative will locate below the x-axis. Then the magnitude of it, you see, it becomes more and more steep. More and more steep means it is further away from 0. So the graph like this. Okay? Then the slope of the first derivative for both of them are negative. So for the second derivative, both of them, the graph will be located below the x-axis. For a graph that concave downwards, for part 1, it is increasing, so it's positive slope, become less and less steep, so it is approaching 0. For part 2, it is decreasing, negative slope for a gradient, for a tangent, and then magnitude becomes greater and greater, hence it is further away from 0. So the slope of the first derivative graph for both of them are negative, hence the second derivative will always be smaller than 0, which means the second derivative will always be negative. Alright, so this is the story of it. Now we come back to the definition for concavity. And by now you should feel that this totally makes sense. You see, when it is concave upwards, concave up means f prime is increasing on I. F prime is increasing, right? If it is concave downwards, means f prime is decreasing. Concave downwards, f prime is decreasing. Okay, So once you get the idea, you should be totally fine with this definition. Alright, and this is what we use to determine the shape of the graph, whether they are a U shape or an N shape. Okay? Now we'll be discussing what happens if the second derivative is equals to 0. Alright? So now we'll look at the definition of points of inflection. So in simple terms, it is where the graph change the concavity, which means it changed from concave up to concave down, or change from concave down to concave up. Okay? So for points of inflection, generally we have three types of inflection points, which is number one, horizontal inflection point, which looks something like this. Okay, if you have a graph like this, which is what we discussed earlier, right? At this point, as you can see, the first derivative is equals to 0, and also if the first derivative is already 0, means you differentiate again, you will also get 0. Okay? Then the second type of inflection point is increasing inflection point, which is something like this. Okay, if you have a graph like this, okay, so okay, maybe I shouldn't draw it like this. It should be like this. Okay. The first derivative, maybe not 0, but the second derivative is 0. This is where it has a increasing point, increasing inflection point. Then the third one is decreasing inflection point, which means it's like this to this. My drawing is not so accurate here, yeah? Like this, okay? So if you notice, for all three of them, it changes the concavity at the red point, right? You see, for the first one, initially it is concave downwards, it's an N shape. Then after the point, it is concave upward, which is a U shape. Okay, this is a U shape, this is the N shape. Then for the second one, from here to here, it is an N shape, concave downwards. From here to here, it is concave upwards, which is a U shape. Then for this, it is a U shape initially, concave up, then concave down. So in order to change concavity, we need to find the point of inflection, and it is a must. Now we'll do a simple activity, which is even simpler than the one just now, right? Again, we need to sketch a graph of first and second derivative of the curve. So for the first one, if the first derivative is like this, that means if the original graph is just a straight line like this, means the first derivative should be a positive constant graph, right? Because the slope is positive. Then if this is a constant graph, if you differentiate again, you will get a 0. Okay? Then for this one, it is negative. So like this. Again, you differentiate a constant, you will get 0. Lastly, it is already a constant, so you differentiate, you get 0. You differentiate 0, you get a 0 again. So what is the point of doing this? This is just to show you that if the tangent line is like that, then the second derivative is always 0. Okay? But this is not what I want to focus, because points of inflection is very easy. You just let your second derivative be 0, you should be able to get the value. What I want to talk about for the second derivative is actually concavity, and another thing, which is second derivative test for a local extrema. Alright, so just now when we talk about the first derivative test for a local extrema, we are looking at the sign, right, from positive, then suddenly change to negative, then we say, oh, we have a from positive to negative, we have a local maxima in the middle, right? Then for second derivative test, if the function is very easy to differentiate, yeah, then we can go for this second derivative test. So let's have a look at the theorem, all right? So if the first derivative is equals to 0, understood because we have a horizontal tangent line, then second derivative is greater than 0, means it is concave up, then f has a local minimum at C. What does it mean? If it is concave up, then we have a horizontal tangent line. The only place that can have such properties is a local minimum, isn't it? Sorry, I shouldn't have done that. Right? It totally makes sense. Then what about this? If the first derivative is 0, understood, horizontal tangent line, then it is concave downwards. Okay, concave down. The only point that can have a horizontal tangent line is this point, which is a local maximum. Okay. However, if both of them is equals to 0, then we can't say anything. Right? So this is all for the second derivative test, and we will see how to use both first and second derivative test. First and second derivative test for the monotonic functions, for the concavity, extrema, and also points of inflection in the next lesson.